We've mentioned calorimetry before, and it's the measurement of heat changes. In the study calorimetry, we use a device that's called a calorimeter. And we've mentioned that briefly before, and we've mentioned before that specific heat of a substance is the amount of heat required to raise the temperature of 1 gram of the substance by 1 degree Celsius, versus the heat capacity, capital C, which is the amount of heat required to raise the temperature of an object by 1 degree Celsius. So the units of specific heat are joules per gram degree C, and the units of heat capacity are joules per gram degree, or just simply joules per degree C. So the heat associated with a temperature change can be calculated this way, one of two ways. Either heat is equal to specific heat times mass times change of temperature, or heat is equal to the heat capacity times the change of temperature. M is the mass, S is the specific heat, delta T is the change in temperature, T final minus T initial, and C is the heat capacity. One of the simplest calorimeters we can use is a coffee cup calorimeter, which we can use to measure the heat exchange for a variety of reactions at constant pressure. And so here's a coffee cup calorimeter. It's a styrofoam cup with a cork or cardboard lid in which a hole has been placed. Then put a thermometer. We've got a stirrer to help mix up our solution. And so since it's open to the atmosphere, it's constant pressure. So some concepts that we need to understand about coffee cup calorimeters. Since we're at constant pressure, we can use Q sub P, and that will equal to the change of enthalpy, state functions. And so our system is the reaction that's taking place. So simply the molecules there are the reactants and the products. The surroundings are the water and the calorimeter and everything else. And so for an exothermic reaction, the system's going to lose heat. The molecules that are the reactants and products, as the converted products, are giving off heat. And so Q system is equal to minus S delta T, minus the mass times the specific heat times the change in temperature. We have to use the negative sign because of our sign conventions, since it's an exothermic reaction. And so the surroundings gain, they absorb heat. And so the heat of the surroundings is equal to mass times the specific heat times the change in temperature. And thus we can put these two together. So Q of the system, the heat of the system, is equal to minus Q of the surroundings, heat of the surroundings. The other type of calorimetry that's used which can actually give us much more precise and accurate results is known as a constant volume bomb calorimeter. And don't be scared when you hear the word bomb. Think of an explosion, and an explosion is taking place. But this isn't shattering into all sorts of shrapnel. It's actually a steel container that's containing the explosion. And so you can see the bomb. It's a stainless steel container in which we put a sample. And there's an ignition wire that we can put it into the bomb that will ignite the reaction when we get going, cause the combustion to take place. There's an oxygen inlet that we will pressurize this with pure oxygen. Now, all this is before we put it into the water. We've got the water, which will measure the change of temperature. We've got a stirrer to help equilibrate the system. We've got this insulated jacket that will help keep the heat inside of our calorimeter. And we've got a thermometer that measures the change of temperature of the water. And that change of temperature of the water is going to be related to the amount of heat that's given off by the reaction that heats up the calorimeter, that heats up the water. And so this, as opposed to the coffee cup calorimeter, which was an open system, this is an isolated system. And so we use bomb calorimeters to determine heats of combustion. So once again, the heat of the calorimeter, Q sub cal, is equal to minus the Q, the heat of the reaction. It's an exothermic reaction. The heat's being given off, and so we have to maintain our sign conventions. So to calculate the Q, do this calculations, we have to know what the Q of the calorimetry is. And so to do that, we have to know the heat capacity of the calorimeter itself. And so the heat capacity times the change in temperature will give us the heat of the calorimeter. And so the heat of the reaction is equal to minus the heat of the calorimeter. Remember, it's an exothermic reaction. The heat's being given off. That's why we have to have the negative sign for the calorimeter, because the heat from the reaction is exiting the system, and going into the surroundings. And so the Q of the reaction is equal to minus the heat capacity of the calorimeter times the change of temperature.